Hello everyone and welcome to this lecture. In the last lecture we saw, in fact in the first lecture we saw a warm up on the graph terminologies, and towards the end I gave you a magic question. The question was related to finding the number of spanning trees in a connected graph. Okay, and then I told you with an example that I draw one matrix, I deleted a row and a column corresponding to one entry, and then I find the determinant of that submatrix, and the absolute value of that determinant was giving you the number of spanning trees. I hope you have verified that number was coming out to be 8. Okay. In this lecture, we will start the journey of proving this beautiful result, and we call it actually Matrix-Tree Theorem. Okay, and I also told you the approach that by selecting n-1 edges out of all the edges, okay, and checking whether this will form a tree or not, and do this for basically all possible combination of n-1 edges. Why such approach is inefficient? Okay, one intuitive way is there are many subset of n-1 edges out of m edges. Suppose m edges are there in the graph. Okay, so these many subset, if you do keep on checking kind of manually or one by one, it's actually fruitless because it is highly inefficient. Then how this determinant will help us? And why determinant is actually efficient? Okay, so there are many questions lying ahead of us. So we will start proving the basically we start the journey of proving the Matrix-Tree Theorem, and there is a disclaimer to it. Disclaimer is this: the journey is actually counterintuitive, but it is very simple. If you have knowledge of 11-12 class mathematics, the simple determinants and its properties, how the row operations, change the determinant or they keep the determinant same, only this much is needed to prove this beautiful theorem. And today for this lecture, I will be introducing a matrix whose determinant indeed will tell you the number of spanning trees. Okay, so let us first start with basically a matrix that we call incident matrix. You might have heard of adjacency matrix, which is very simple matrix, n cross n matrix, where if vertex I and j have an edge, we will put 1 in the ijth position of the matrix A, otherwise 0. So very simple matrix. Today we will see another matrix which is called incident matrix, another interesting matrix. Okay, and this will later on help us in proving the Matrix-Tree Theorem. Okay, so incidence matrix. Incidence matrix. Okay, very good. So I will take the same example I took in the last lecture, first lecture. Okay, so sorry about this. So suppose there are 4 vertices in my graph, and this is the same edge. Okay, same edges, same graph. In fact, 1 2 3 4. Very good. Now let me first draw the incidence matrix. Okay, and then what you will meanwhile you keep on thinking what exactly I am doing. Okay, so incidence matrix will be something like this. Okay, so in order to first draw or write the incident matrix, what I will do, I will give some signs to some direction to the edges. Remember, your input graph is still undirected. I am deliberately giving some direction to the edges. Okay, and they are arbitrary direction, and then I am writing the incident matrix. Suppose I denote this matrix by Q. Okay, sorry, this will be my 4 cross 5 matrix. 4 is the number of vertices, 5 is the number of edges here. Okay, so let me first write down, and meanwhile you keep on thinking what I am doing, and let me actually number these edges also. Label these edges: E1, E2, E3, E4, E5. Okay, so and these columns I will be indexing by these edges E3, E4 and E5. Okay, so what I will do is, okay, I will check E1 is coming out of 2, this is originating from 2, so I will put 1 here, ending at 1 I will put -1 here, and 0 0. E2, I am coming from 3, so 3, then ending at 2 minus 1, 0, 0. By now you might have now guessed what I am actually doing. Now for 3, what will be coming out of 4, going to 3, this will be 0, 0, E4, coming out of 4, again going to 2, minus 1, rest of the place 0, 0, E5 is coming out of 4. Oh, out of 4 there are many edges coming. Okay, 4, and then going to 1, 0, 0. Now let me define what incident matrix is for a general graph. Suppose in a graph there are n vertices, okay, and m edges. Okay, the incidence matrix is of n cross m matrix, let me denote it by QG of graph. Okay, so G have n vertices, m edges, so this is nothing but an n cross n matrix, and let me denote its general element by Qij. Okay, so this matrix is nothing but n cross m matrix where Qijth entry is equal to 1 if the edge Ej is originating spelling is wrong. Okay, sorry, originating at I. Okay, it is minus 1 if terminating at I. If Ej is terminating at vertex I, okay, and otherwise it's 0, very simple matrix. Okay, so what could be the properties of this matrix? Okay, let us see some very obvious properties. One thing is for sure, if you pick any column, in any column the columns are corresponding to edge. In every edge there are 2 endpoints. At one endpoint we are putting 1, another point we are putting minus 1, depending upon the direction, and rest of the entries are 0. So if you add all these entries of the column, it will give you 0. Okay, so very simple observation. Now the next very nice property of this matrix is this. And remember, in the last lecture towards the end I draw one matrix. Okay, the matrix was, let me draw this matrix again, then we will see the relation between that matrix and the incidence matrix. Okay, so let me draw this matrix again. Before going ahead, let me check if I missed something. No, everything is going very well. So now let me draw this matrix I draw in the last lecture. Okay, so the graph was same. I will keep on drawing this graph again and again. So 1, 2, 3, 4. Now remember, I draw the last graph as this, last matrix as this in the last towards the end of the last lecture. So it was 2, then yeah, minus 1, 0, minus 1, then 0, minus 1, then it was 3, minus 1, minus 1, and this was minus 1, minus 1, then it was 2, minus 1, minus 1, 3. This matrix is nothing but the famous Laplacian matrix, and we will denote it by L. Okay. Now the next interesting result is this. Irrespective of the incidence matrix you take of a graph, right? Remember, the incidence matrix is depending on what the direction you give to edges, right? Irrespective of the incidence matrix, if you multiply the incidence matrix by its transpose, it will always give you the Laplacian matrix of the corresponding graph. Okay, why this is true? Why this is true? Okay, so if you see, I mean, this is very easy to observe that. By the way, okay, so let us first prove this, why this is, and let us call the general element of this is Lij. Okay, what is Lij? what is Lij? If you see, okay, so what Laplacian matrix is actually, so then we will see actually what, why this is relating to Q into Q transpose, okay. So Laplacian matrix actually we can also write in terms of something called D minus A we know that it's an adjacency matrix, so negative adjacency matrix. If you add that negative to the D matrix, D is your diagonal matrix where on the diagonal there are only degrees. So if you see that these are the degrees, right, these are the degrees D, and the rest of the entries are -1 or 0 in the off-diagonal, and this is nothing but minus A. If you adjacency matrix on the diagonal there are zeros, and if vertex I and j has an h, we will put 1, otherwise 0. So this is the negative A. If you add to degree, if you add negative A with D, it will give you the Laplacian matrix. Now what? So suppose this Laplacian, the general element is Qij, okay. So basically we have to prove that y, so y Q into Q transpose will always give you Laplacian matrix, very famous matrix, okay, irrespective of the direction of the edges you give, okay. Now if you see in general, what is Qij? Qij is nothing but, so basically if you see here, Qij is nothing but dot product of, it's actually dot product of the ith row of Qg with the qth row of the Qg, right, with the qth row of capital Qg, sorry, yeah, very good, capital Q. This is very easy to weigh just by this, okay. So the Qij, or in fact suppose I mistake, I mean, so this is Lij, I would say, sorry about this, Lij, okay, sorry about this. These notations are very, we have to take very careful, we have to be very careful, yeah. So Lij, very good. It's a dot product of ith row of Qg with qth row of Qg, okay. Now if you see, when I and j has, between I and j has an edge, right, so what will be the dot product? Suppose if you take here, suppose vertex 2 and vertex 3 has an edge, right, is there an edge? Yes, is there an edge which is equal to E2? So corresponding places, at one point it will be -1, at one place there will be 1 here, right, towards the end, and rest of the entries here, because there can be at most one edge, there can be at most one edge between any two vertices. So at one place it will be 1 and otherwise 0, at 1 minus 1, sometimes there are on the both end places it will be 0, right. So only corresponding to where there is an edge we will have 1 and -1, otherwise there will be at least 1 0, right, corresponding. So this dot product will be -1. What happens when I equal to j? And by the way, if there is no edge, right, it will be by default 0, because at least at one entries there will be zeros, right, at least one, because the edge is not at all, no edge is there is no edge between vertex I and j, okay, very good. So what happens when I equal to j? Okay, so basically the diagonal entry, or what you call the diagonal entry of L, right, so this will be when I equal to j, is it nothing but dot product of I with itself, right, dot product of I with itself is same as number of edges incident on it, right. So the edges, when the edges are incident on vertex, so what will be the entries? Either it will be 1 or -1, but if you take dot product it will give you 1, right. So the total sum of ones will actually give you the degrees. So it is very clear, right. So from here, so this implies that Q transpose Q is indeed Q transpose Q Q into Q transpose is indeed L. Very simple fact, okay, very good. Now next thing is about, like we have seen a property of incidence matrix. If you add any, you pick any column, you add all these entries in that column, it will give you 0, right. What about L? What about L? L, suppose, is your this matrix L11, L12, L1n. Remember, these L1s are that on the diagonal there are degrees, right? So Ln1, okay, L, and ideally I should have, pictorially represented as in the square form, okay, because this is a square matrix. This is n cross n matrix, whereas your Q is what? N cross m matrix, right? N cross m matrix. Very good. So this is what could be the properties? One property is what? That you see here, this is a symmetric matrix. This is a symmetric matrix, okay? Symmetric matrix. One property is. Another property is what? Like Q, you pick any column, add all these rows, it will give you 0, right? But this also happens for rows also. If you pick any row, add its column, it will give you 0 because it's a symmetric matrix, okay? So column sums and row sums are equal here. It is giving you 0 vector. Very, very simple fact, okay? Now there is one more thing that we will utilize many lectures later. This matrix, if you pick any vector, okay, x, and multiply its transpose on the left hand side and multiply with itself on the right hand side, this quantity is always greater or equal to 0 for any x, for any vector x, okay? Remember, by vector I mean some column vector by default, okay? So you pick any vector x, you multiply with on the left hand side you multiply with transpose on the right side with itself. This will give you greater or equal to 0. Why this is true? Very easy to follow from this property, right? L you can write as Q into Q transpose x, right? Then this is nothing but this transpose times this. Now this is a vector, right? And vector times its dot product is always greater or equal to 0, okay? So this is actually called positive semi-definite matrix. For whatever matrix, if this happens, that x transpose AX, suppose, or MX, whatever this matrix is, if this happens, then M is said to be positive semi-definite matrix, and these matrices displays very beautiful properties. So L will also display very beautiful properties. You will see after some lectures, but for the time being, I think this information is not needed because we are in the hunt of proving Matrix-Tree Theorem. So now, and we will be only using this row sum and column sum is 0, okay? Now the last thing about this lecture will be proving a fact that, and it again about the Laplacian matrix. Remember, in the last lecture towards the end I picked one entry, delete its row, column, the resulting matrix whatever it was, I calculate the determinant, and I saw that it was coming out to be, I think, plus or minus 8, okay? The mod of this entry or the absolute value of this entry, I said it is giving the spanning trees, okay? Actually, you can, I said that you can choose any entry. That was the magic, okay? We will prove that it doesn't matter what entry you choose, the answer is always same. And what was the determinant? What we call such quantity? Such quantity we call cofactor of that corresponding entry, okay? That entry that we have removed, right? So the next result is cofactors of, or maybe you can write in other word, any cofactor of L is same. Any cofactor of L is same, okay? Let us prove this beautiful fact, okay? Prove, okay? Cofactor is what? Basically, you suppose cofactor of entry Lij, you pick that entry, you delete its row and column, okay, you take the determinant of the resulting matrix and multiply that determinant with minus 1 to the power I plus j. This is the sign, okay. So let us now write the Laplacian matrix, okay, and so suppose this is L11, L12, okay, and that's L1n, Ln1, Ln2, okay. I will prove that the cofactor of this guy and L21 are same, and rest of the entry actually, so similarly you can follow the same proof, okay. So why cofactor of L1 and L21 are same? So cofactors of L11, okay. What is cofactor of L1? It is nothing but minus 1 to the power 1 plus 1, this is sign rule. Then what you do, you delete the first row and first column, right? First row and first column, the first row after deleting first column and first row, so the matrix will be this, right? L22, L23 and L2n, very good. Then Ln2, Ln3, then Lnn, okay, very good, okay. And then what? Yeah, and similarly what will be the cofactor of L21? Cofactor of L21 is nothing but 2 plus 1, okay. These are very actually 11, 12th class stuff, okay, but still for the recap purpose I am doing it. So now what I have to do is I have to delete the second row and the first column, okay. So second row deleting, so this will give you 1 2 1 3 and maybe this L1 and so on, and this will L12 and then Ln3 and Ln. Let me write the another row of this. So this will be nothing but 3 2 L33, okay, L3n. Similarly here this will be L32, L33, L3n. Now remember, from here to here all these are same matrix, okay. We have to prove that, and then we have to prove that, no, so we have to prove that actually the determinant of this, right, sorry about this, determinant of this matrix are actually the same, okay. Now if you see, we can actually make use of the properties of Laplacian matrix, right, to actually prove that these two cofactors are same. What could be those properties? Okay, now remember, in this matrix, right, in this matrix, if you select this part, right, and suppose this row is R1, this row is R2, okay, and this row is Rn, what will be their sum? This will be giving you this 0 0 0 0, right? This will be giving you 0 0 0 because of the properties of Laplacian matrix, okay. That means what? If you, yeah, so only the difference between, suppose if I add these rows, or maybe if I add all these rows here, suppose this is what corresponding to R2, right? If you see that this is R3 and so on and Rn, what will be the sum of this? What will be the sum of this? Sum is nothing but negative of R1 due to here, negative of R1. Now do what? Now what? You add all these rows, and replace the first row of this by the negative of R1. So you can replace this by negative of R1, right? Negative of R1, okay. Now we know from 11 and 12th class, by these row operation, determinant does not change, okay. You are adding basically there some combination of edges to some rows to some other row, the determinant does not change. Now you see that these two matrices are same. So basically minus R1 is here, and then these matrices are already same, right? Now only the thing is, here it is, this is R1, R1 and this is minus R1, but this minus thing is actually taken care of this sign rule here, right? Hence we can see that determinant is actually basically these two cofactors are same, right? This implies that cofactor of L11 equal to same as cofactor of L21, and similarly you can prove that cofactor of any Lij. Okay, any Lij. Okay, very good. So this lecture was again very simple one. We studied incident matrix, its properties, incident matrix times its transpose, always giving you Laplacian matrix. Laplacian matrix displays some beautiful properties, and one result on Laplacian is that any cofactor of Laplacian is same, and we will prove that in the next lecture onwards that this cofactor is indeed the number of spanning trees in a graph, in the corresponding graph. With this, I am stopping this lecture. Thank you very much, and lot of exciting things are ahead of us. Very good. So see you in the next lecture.